Here are more examples on graphs of motion. I'm going to show you once again how to go from displacement time to velocity time to acceleration time, and I'll show you the reverse as well. So let's do this. Okay, suppose I've got the following displacement time graph. So time is typically always on the x-axis because that's where your independent variable goes. So that's where the variable that's changing goes. Okay, so time is changing, and displacement, suppose displacement is what you're measuring. That's the dependent variable that goes on the y-axis. Suppose in this case it's meters. And let me draw a sketch like this. Here are some numbers. Okay, here's the following graph. I want to go from this to a velocity time graph. Time, once again, is on the x-axis. Velocity, meters per second. Now, first things first, you break this graph up into segments, so into the shapes that you can see. So you can see there's a triangle there. Let's call that area 1, rectangle, area 2, and another triangle, area 3. Okay, the time stays the same. So 0, 5, 10, 15. Remember, the time is always the same. We're just using what we know to work out what the other quantities are. So in this case, velocity. So how do we go from displacement to velocity? Well, we know that velocity, v, is distance or displacement in this case, divided by time. That's our formula we need to use. So in other words, for segment 1, the velocity v is displacement, which is 60 in this case, divided by time, which is 5. 60 divided by 5 is 12 meters per second. So the velocity is constant. So 12 is here. From 0 to 5, it's constant like that. Now, number 2, velocity v is 60 once again divided by, be careful here, between 5 and 10, there's 5 seconds. 60 divided by 5, and that is also, what am I doing? No, this is 0. Okay, even I get sometimes carried away. The velocity is 0 from 5 to 10 seconds because if you're moving from between 0 and 5 seconds, then you come to a stop and you stay there for 5 seconds at the 60 meter mark, your velocity is 0. You're not going nowhere. So it drops down rapidly. Let me use a different color. Blue. From there, from 12 to straight down to 0. So this is a step diagram. So after 12 meters per second, you come to a halt here for 5 seconds. So it goes straight down to 0. That's your velocity, 0, for 5 seconds. Now, velocity for the velocity for area 3, that's 60 once again, divided by 5, which is 12 meters per second, in the opposite direction. Remember, in maths, if you have a line like this, it's a positive gradient, positive slope. A line like this has got a negative gradient, negative slope, so it's a minus. So that's why you draw a plus and minus y-axis. So you have a minus 12 down here, meters per second. It's the same speed, but in a different direction, opposite direction. So after 10 seconds, it drops back, goes back up to 12, flat line, constant, and it goes back to 0 after 15 like this. Okay, because it goes from 60 meters down all the way back to 0, and at 0 there's 0 speed, so 0 meters per second. Okay, I'll say it again. After going 12 meters per second, it goes back to 0 because it's a line where the distance is going from 60 down to 0, and at 0, velocity is 0. So let's go now to an acceleration time graph. Time, seconds, acceleration, meters per second. You don't have to write the arrows on top, but I do because in physics, when you get used to doing things like using vectors, you put arrows, but you don't have to put arrows on top. But anyway, meters per second squared. It's just a nice habit. just so you understand what you're doing. Now, if you look here, this is actually easy because the acceleration, if something's moving at 12 meters per second for 5 seconds, it's moving at constant velocity. It's a flat line. Your acceleration is 0. So from 0 to 5 seconds, it's 0. Similarly, if you're not moving at all, your velocity is 0. For another 5 seconds, it's 0. Acceleration. And once again, if you're moving at constant velocity, it's 0. And beyond that, it's 0. So that is your acceleration time graph. And you can check your answers. All right, just think logically. If my acceleration is constant, if it's a flat line, if my velocity is constant at a flat line, it means my acceleration is 0 because I'm moving at constant speed. And by definition, acceleration is how much your speed is changing. So if it's not changing, your acceleration is 0. Let's now go from acceleration time to velocity time to displacement time. Okay, let me give you this. Time in seconds, acceleration, meters per second squared, 2, 0, minus 2, 1, 2, 3. Okay, suppose you have a flat line like that, then you have this, and then this. I'll put 4 seconds as well. Okay, how do I go from here to a velocity time graph? Okay, first of all, let's draw a sketch. Time, seconds, V, meters per second. Okay, let's break this up into segments now. If you look here, segment 1, okay, by definition, acceleration, so you have to use your logic and intuition and also the formulas that you know. Acceleration is the change in velocity over time. Now, to find velocity in this case, let's leave out the deltas for now. You do acceleration times time. So from 0 to 2 seconds, the acceleration is 2. So it's 2, A is 2, and the time is 2. So the answer is 4 meters per second. That's your velocity. Okay, for an acceleration of 2 meters per second squared for 2 seconds. So let's put on this graph here. Now, what would this line look like? Now, because you can't use a flat line and put 4. Well, because the flat line means you're moving at constant velocity. And if you're moving at the same velocity, you don't have any acceleration. Because acceleration means the change in velocity. You have to have a change in velocity. So it has to be a straight line with a positive gradient like this. So 0, 1, 2, 3, 4. So you have to think of this intuitively as well. From 0 to 2 seconds, you've got a velocity of 4. So it goes like this all the way to 4. Let's put 4 up there. Okay, let's go by ones. 3, 2, 1. Okay, from 0 to 2 seconds, the velocity is increasing to 4. Okay, there's a change in velocity, and that gives you the time. You can check your answer by finding the gradient, because acceleration is velocity over time. If you do 4 divided by 2, yes, you get 2 back for the acceleration. So that's how you check your answers. Okay, what about 2 to 3 seconds? What's happening here? Well, here, if there's 0 acceleration, it means the velocity is constant. Right, remember what I said before? If you're moving at the same speed, your acceleration is 0. So it stays at 4 for the next 2 seconds. For the next second, sorry. So between 2 and 3 seconds, the velocity stays the same. Okay, what's happening over here between 3 and 4 seconds? Between 3 and 4 seconds, the velocity is going back up again. Oh, sorry, the acceleration is going back up again to minus 2 meters per second squared. Okay, so it's decelerating, in other words. If you're decelerating, your speed is decreasing, right? Think of the car and the pedal. If you slam the brakes, you're decelerating. So in other words, the 4 drops back down in a straight line. And that's how you do it. That's how you go from the acceleration time graph to the velocity time graph, okay? So in other words, going back to summarizing again, region 1, if you're accelerating at 2 meters per second squared, you're accelerating, your velocity is changing. So therefore, it's a straight line with positive gradient going up. Between 0 and 2 seconds, your velocity is 4 meters per second. And then your acceleration drops to 0. If you slam the brakes, if you take your foot off the accelerator, you're moving at constant velocity, you stay at 4 meters per second, and then you slam the brakes, you decelerate, your velocity decreases. So let's now go to displacement time. Displacement meters, right? Okay. How is displacement and velocity related? Well, velocity is displacement. In other words, speed is displacement, displacement in this case, divided by time. In other words, displacement is velocity times time. So it's the area under this graph here. If you look here, break it up into sections, remember? There's a triangle there, rectangle there, and another triangle. Okay, if you look here for the first triangle, your displacement is, so velocity times time. It's the area, velocity is 4. Oh, sorry, the area under the triangle, the area for, let me do it here. I'll do it down here. Okay, the area for 1, so we need to work out the area because displacement is velocity times time. Velocity is, so the area of a triangle is a half BH, half times base. Base is 2, right there. And the height is 4. So 4 times 2 is 8, half of 8 is 4. 4 meters is your displacement. Okay, now for area 2, let's work out the areas first. Rectangle, area of a rectangle is length times height. The length of this is 1, okay, because 3 minus 2 is 1. And the height is 4. It's still 4, so it's just 4 meters. And then area 3 is a triangle again, half BH, half times the base is 1. Be careful here, because 4 minus 3 is 1. And the height is 4. So a half of 4 is 2 meters. So how do we interpret this? Now, we need to be careful. Let's go back to the graph. So 0, 1, 2, 3, 4. The time stays, right? Go back to the acceleration time graph next. Now, the object is accelerating from 0 to 2 seconds. Therefore, the displacement will look like a curve because acceleration means you're covering lots of ground very rapidly in a non-linear fashion. So from 0 to 2, so you've got 4 meters there, right? Calculated for the first segment. 0 to 2 should look like this, a curve increasing. Okay, up to 4, right there. And then between 2 and 3, so the second segment, the acceleration is 0, but the velocity is constant. Okay, so another 4 meters after that, it's going in a straight line, linearly, in a linear fashion. And then 2 meters, so for segment 3, it's increasing, it's decelerating, I should say, but the displacement is 2 meters, so it goes back down linearly like that. Remember, displacement is how far you are from your starting point. So this is telling you these numbers here. You're moving at 4 meters away, and then another 4 meters, but then you're decelerating, which means you're changing direction to go back to where you started, another 2 meters back. So that's why it's looking like this. It goes up, it's accelerating, then it continues at constant velocity, and then it drops back down. Okay, for these time periods, and that's how you go between these graphs. If you practice more, you get more efficient at these. So I suggest you practice a lot more and visualize what's happening. Always think of a car that's moving, and that'll help you hopefully understand it better.